All right. So today we'll get going again on chapter 17. Okay. Right, we haven't really talked about chapter 17 since a week and a half ago or so, right? Okay, we're gonna do chapter 17, talking about titrations and um, solubility product equilibrium over the course of this week and Monday next week. Then we'll talk about thermochemistry for 2 days worth of lecture, right? And then we'll talk about electrochemistry, and that's it. Okay, so that's kind of what we have for this semester. Okay, so again, finishing up chapter 17, talking about titrations and solubility equilibrium. And then we'll talk about thermochemistry, and then we'll talk about electrochemistry. Okay. And we'll finish up all that stuff before Thanksgiving break. We'll have a regular exam after Thanksgiving break on the rest of the stuff on chapter 17, thermochemistry and electrochemistry. And then our final will be the following week. I forget the day off the top of my head, right? We'll talk more about that when we get closer to the actual final exam. Okay. Right. So any questions about anything related to the course before we get going here today? All right, just as a reminder, right, we're talking about in chapter 17, we're talking about buffer solutions, right? Buffer solutions were solutions that contained a weak acid with its conjugate base. For these buffer solutions, right, we could use the Henderson-Hasselbalch equation to solve for the pH, right, which was pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid, right? And that type of stuff is going to be related with titrations here as we talk about different phases of a titration, right? So titration, if you haven't done one in a lab yet, you will, right? Right? Okay, so there's a question here on Zoom real quick. How many points was on the curve? That I do not remember off the top of my head, but it was similar to the first exam. But again, I don't know. Yeah, what that is off the top of my head. For those who took exams in class, you can kind of figure that out based off of your total score and then your curved grade on Canvas. Those who took it online, you can look at your online exam score versus the curved grade on Canvas to kind of figure that out. I forget off the top of my head what the curve came out to be. Yep. It was similar to exam one. All right. So again, so titrations, right? Titrations, you have right, 2 different solutions that you're mixing together. You have some sort of solution that has a known or unknown, and then you have your titrant. Okay, so you have something in this graduated cylinder that you can very accurately measure the amount of volume of that you've added to your solution. Okay, and what is done, right, is you slowly add the titrant to your solution, and some chemical reaction will take place. In this case, you have an acid-base reaction occurring, right? And then in this example here, this acid-base reaction is occurring, the pH is changing. At some point, the pH changes such that the indicator in this solution changes color, right? And then you know if you reach some sort of endpoint, some sort of equivalence point that we'll talk about, right? And that will allow you then to calculate concentrations of unknown things and such, okay? It gives you some information about what had happened in your titration. Okay? That's kind of the general idea of a titration, so let's get into specifics. Okay, so there will be different phases of the titration that we'll talk about. Right, the initial phase, right, where you just have your solution of an acid or a base. We're going to talk about just acid-base titrations in this class. You can do titrations with different types of chemistry, electrochemistry, or other things, okay, but we won't do that here. let's focus on acid-base titration, okay? So we'll have some solution with some amount of an acid or a base, right? That's our initial phase. Then we have some partial neutralization where we add, let's say we start with an acid, right? So we start with an acid, we're going to add some amount of a base to that solution, and that's going to partially neutralize that acid, right? Because the acid and bases will react together to form a salt in the water, right? So that will be some partial neutralization, okay? I get then to the equivalence point, right, which when I have complete neutralization by acid, where I've added equal amounts of an acid and the base in solution, right? So I have some acid in solution, I add equal amounts of the base so that they completely react with each other. And that's why it's called the equivalence point, the equivalence point, right? Because again, you've added equal amounts of the acid and base in that solution, right? So you have equivalent amount of acid and base. That's the equivalence point, right? And then after that, you just keep on adding your titrant. In the example, right, I'm giving here, I'm adding a strong base. So I keep on adding strong base, and I'm just diluting then that base, right? Because I'm adding that base to a solution that is now just water and a salt. So that base isn't reacting with anything. It's just going to be diluted as it gets added to the solution, right? So those are the different phases of a titration, okay? And there's different types of titration we'll talk about: strong acids, strong bases, strong acids, weak base, weak acid, strong base titrations, right, and polyprotic acids, okay? And what these titrations will look like, okay, and these different phases will look like will depend on what we're doing, okay? So we'll first just focus on strong acid, strong base titration, okay? So in strong acid, strong base titration, I say start off with a solution of hydrochloric acid, and I'm titrating it with sodium hydroxide, okay? Right, so when I add the sodium hydroxide to the hydrochloric acid solution, right, I'm going to react those two things to form a salt, sodium chloride, and water, right? Okay, and so this is the titration curve. Okay, so this curve plotted here on the right of the slide, right, is called the titration curve. Okay, right, we see that initially, right, on this curve, the x-axis is the volume of strong base, right? My titrant is, the volume of your titrant is going to be on that x-axis. Okay, so in this case, it's the volume of sodium hydroxide. That's my titrant, right? The y-axis is going to be pH of your solution. Okay, so when I don't add any of my strong base, right, I just have the strong acid solution, right? I have a very low pH, so I have a strong acid sitting in solution, right? And then as I add that base, I'm going to remove some of my strong acid through this chemical reaction described here, right? So my strong acid will react with the weak or strong base that's being added, form a salt plus water, right? And so I increase the pH slowly as I'm adding some amount of my strong acid or strong base to solution, okay, until I reach equivalence point, right? We're at equivalence point. Again, I've added equal amounts of sodium hydroxide as hydrochloric acid in solution, okay? Right, and so that means that all my hydrochloric acid reacts with all my sodium hydroxide, right, to form just sodium chloride and water, right? And sodium chloride does not affect the pH whatsoever, right? And so this solution then becomes a neutral solution of pH 7, okay? So the equivalence point for strong acid, strong base titration always has a pH equal to 7, okay? And that's because the salt that you form does not affect the pH, right? When you talked about pHs of salt solutions, right? Sodium ions and chloride ions do not do anything to change the pH of your solution. They're just spectator ions, just floating around, doing nothing, okay? And so the solution will have a pH of 7 at equivalence point, right? Because again, at equivalence point, I've say added 1 mole of hydrochloric acid, added 1 mole of sodium hydroxide. So those things completely react with each other, form 1 mole of water and 1 mole of sodium chloride, right? And so I have no more acid, no more base left in solution. I just have my salt in that solution, and the salt does not affect the pH. So I have a pH of 7 for a strong acid, strong base titration. Okay? And then after that point, I'm just adding strong base to the solution, so the solution then becomes very, very basic. Okay. We see, right, that the pH change is very gradual until I get near this equivalence point, and near that equivalence point, you then have a very strong, drastic change in pH. And this is going to be true for all of the different types of titration, that near the equivalence point, the pH change is the greatest at that point, right? And so if I have an indicator in my solution that changes color at around a pH of 7, right, then right before I reach equivalence point, my indicator is going to be one color. Then right around equivalence point, right, my pH is going, or my indicator is going to change color, right? Because if I were to like zoom in around this 50 milliliters of sodium hydroxide added, right, that just barely to the left of 50 milliliters, I'm one color, barely to the right of 50 milliliters, I'm going to be another color, okay? And so this color change of my indicator will tell me that I've essentially reached the equivalence point, right? So the fact that the pH changes very drastically around the equivalence point is why we can often use indicators that just change colors in these titrations to tell us when I've reached equivalence point, right? Because if equivalence point is corresponding to some gradual pH change like this, right, an indicator that has a color change over, you know, a pH range of like 1, right? Let's say my indicator's color change was at a pH of 1.5 or something, right? Then I would have a much more difficult time telling when I've sort of reached a pH of 1.5 because the color change would be a lot more gradual, okay? But for an indicator that's a pH change or a color change at pH of 7, right, that color change is going to be drastic because the pH change is very drastic near that equivalence point. Okay. So questions about this pH curve, the separation between a strong acid and a strong base. All right. So typically when we're solving problems dealing with titrations, trying to calculate pHs and things of that nature, okay, first need to do some sort of stoichiometry type calculation, determine what components I have in excess, what limiting reagents I have, right, and have those reactions go to completion, doing something like an initial change final type chart, like IC chart, right? So again, right, for the strong acid, strong base titration, right, I add some base to my acid solution, I have this reaction, right? So in order to figure out what is the pH of the solution, I got to figure out what's in the solution. So first, I got to have this reaction go to completion. And to do that, I need to calculate how many moles of hydrochloric acid I have and how many moles of sodium hydroxide I have, figure out what is my limiting reagent, and then what's left after this reaction goes to completion, right? Okay. And then once I know what's left after the reaction goes to completion, right, then if there's some equilibrium established, and I got to do an ice table and figure out the equilibrium, right? Maybe there's a buffer solution. I use a Henderson-Hasselbalch equation, or maybe I have something like this, right, where I have a strong acid, strong base, and there's no equilibrium, and I just need to know what is the concentration of my acid or concentration of my base that's left in solution to figure out the pH, right? So again, for these titration problems, again, the two major steps is the first step, figure out, right, what's reacting and react things to completion, and then figure out, based off of what's left in solution, how I calculate the pH, okay? Which again, could be an ice table, could be a Henderson-Hasselbalch equation, could be just using concentration of your acid or your base, okay? So let's do an example, right, of looking at the pH for the titration, right, of HBr, a strong acid, with NaOH, a strong base, okay? I want to know what is the pH, right, after I've added the following volumes of my strong base, my titrant, okay, to the solution, right? And I start off with 20 milliliters of 0.2 molar HBr and adding some volume of 0.2 molar NaOH. Okay. So, right, for those in class, right, hopefully picked up examples on the way in. Otherwise, the examples are in the back table. Okay. Also available online. And they were handed out Wednesday for those who are in the Wednesday's lecture and are attending online. You can always pull that out and work it out with us. Right. Right. And so the reaction that's going on in the solution, right? I have HBr, my strong acid, and I'm reacting it with my strong base in solution, right? And that's going to form NaBr, just some salt, plus H2O. Okay. Right, now I have, right, for each one of these different volumes of NaOH, right, my volume and the concentration of HBr is always the same, okay? Which is the number of moles of HBr is equal to the concentration of HBr times the volume of HBr, right? Concentration is moles per liter. So you take your concentration, multiply it by your volume in liters, and you get your moles, right? So the number of moles then of HBr is 0.2. Now I'd have to convert this to liters because, again, concentration unit here, molarity, is moles per liter. So this is going to be 0.2 for the concentration times 0.02 for the volume, right? The volume is 0.02 liters, right? Divide 20 by 1,000 and you'll get 0.02 liters, okay? And so my number of moles, right, of HBr is then 0.004 moles, okay? So that is the number of moles of HBr in that solution, okay? That's the same every time, right? No matter what volume of my strong base I add, that is the number of moles I started with, right? That's going to react with the strong base that's added in that solution, okay? So let's say, right, we add, let's do the 15 milliliters example, right? So initially, right, I have 0.004 moles of HBr. I've added 15 milliliters of my strong base NaOH. That's 0.2 molar, right? Okay. So again, getting the number of moles of my strong base NaOH is just the concentration times the volume. Concentration is 0.2. The volume is 0.015. Okay. So this number of moles is 0.003, right? So moles, okay, of HBr and NaOH, okay? Right. So right now I'm just looking at 15 milliliters of NaOH being added. So that's how I get that number of moles of NaOH is I used 15 milliliters times its concentration to get the number of moles, okay? So questions so far as to what we're doing, how we did it? Right? And so now these two things are going to react with each other. They're going to go to completion, right? My limiting reagent is what? NaOH, right? I got less NaOH, so that's my limiting reagent. So I'm going to lose all of my NaOH, right? I'm going to gain equivalent amount of my salt and water. Don't really care about those. We really don't even care about the salt, right? NaBr, again, is just a salt that has a bunch of spectator ions, sodium and bromine or bromide, right? Are both just this ions that are going to float around in solution, not affect the pH. So don't really even care about that, okay? Right? And so what's left then is 0.001 moles of my strong acid, HBr, and 0 moles of my strong base, NaOH, right? And so to get the pH of this solution, right, the pH of my solution is going to be determined by what? What what species in solution, right, from this reaction is determining the pH after things have reacted? By what? Yeah, HBr, right? Because that's all, right? What's left in solution is HBr, NABr, and H2O, right? Water's not affecting the pH. NABr is not affecting the pH. The only thing that changes the pH is HBr, which is a strong acid, right? So all I need to know is what is the concentration of HBr, right? Because the concentration of HBr equals concentration of H plus, okay? Right, because this is a strong acid, so it fully dissociates, okay? And if I know the concentration of H plus, I can get my pH, right? Because the negative log of the concentration of H plus is going to give me the pH, okay? And so the question is, what is the concentration of HBr, right? Well, the concentration of HBr is its moles divided by the volume, okay? So the concentration HBr is equal to the moles of 0.001, right? That's what we figured out. The moles of HBr left. And then the volume, right? Well, my volume is the total volume of the solution, right? I have the initial volume of HBr plus the volume that was added with sodium hydroxide. So it's going to be the 20 milliliters plus the 15 milliliters to get me a total volume of 0.035 liters. Okay? So that is going to give me the concentration of HBr. Okay. I have worked out. No. All right. So the final concentration, HBr, is equal to 0.0286 molar, okay? Which that is a concentration of H plus, and so the pH is just the negative log of 0.0286, okay? Which gives us the pH is equal to 1.54. Okay, so that is the pH of our solution after 15 milliliters of sodium hydroxide have been added. Okay. Questions about this example so far? All right, so again, the two phases in this problem were first react everything, and then look at what's left in solution and figure out what's determining the pH. And then after that, right, calculate the pH. In this case, we had a strong acid. So all we had to do is figure out what is the concentration of that acid to figure out the pH, okay? But often, right, at this stage, you're going to have to recalculate concentrations because now you've changed the volumes of your solution, right? And so you'll dilute things, and so your concentrations will change. Okay? So we'll do at least one more of these right now. The pHs of all of these are posted online. But so let's look at the 20 milliliters example, right? So at 20 milliliters NaOH, right? I have that same reaction, HBr plus NaOH going to NaBr plus H2O, right? So in this case, right, my initial number of moles here of HBr is still the 0.004 moles. NaOH, I now add 20 milliliters of a 0.2 molar, right here, right, 0.2 molar NaOH solution, okay, which means its concentration, or its number of moles as well is going to be 0.004 moles, okay, right, and so, right, these have equal amounts, so both of them are going to drop and fully react by 0.04 moles, right, and at the end, I'm going to be left with none of that, right? I'll be left with 0.004 moles of sodium bromide, which again is a neutral salt, right? And so for this, at 20 milliliters, right, there's nothing in here that's affecting the pH. So it's just the pH of a neutral solution, right? So we have a pH equal to 7, right? And again, this 20 milliliters is then defined as the equivalence point, right? My equivalence point is when I've added equal number of moles of my acid and base together. Now, it happens to be that I have equal volumes added, but that's because the concentrations of my acid and of my base equal each other, right? So the equivalence point does not mean the equal volume of acid and base, right? It means equal number of moles, right? Again, in this example, those are the same thing, just because the concentration of my strong acid and of my strong base happen to be the exact same concentration. But if they weren't the same concentrations, right, then the equivalence point would not be at the same volumes. Okay? Right. And then, right, the pHs at all these other ranges, right, are doing the same thing, right, setting up this stuff, figuring out what's left. And when it's a strong acid, strong base, it's just then calculate the concentration of the acid or the base that's left, and then use that to get our pH. Okay. Questions about how to do this example, okay, this procedure here? For the paper here. All right. Let's pretend instead what I have is, let's say I had a 20 milliliter sample of 0.200 molar HBr that is titrated with 0.1 molar NaOH. Okay. What volume of NaOH must I add to reach equivalence point? Right, to reach the equivalence point, right, in this solution, right? So I have some sample, right, of 0.2 molar HBr titrated with 0.1 molar sodium hydroxide. And the question is, what is the volume of sodium hydroxide that I have to add to reach the equivalence point, right? Yeah, so the answer will be 40 milliliters, right? But if you don't, right, if it's not easy to see that right away, right, again, the definition of equivalence point is what? When I've added equal amounts of what? Right, of base and acid, and specifically the number of moles of the acid that you add equals the number of moles of your base, right? NaOH, right? Number of moles of your acid equals the number of moles of your base, right? That is equivalence point, right? That is what it's defined as, right? When I have equal amounts of acid and base in solution. Okay, so again, NaOH, HBr, okay, right? And then again, the number of moles of HBr is related with the concentration of HBr times the volume of HBr. And the number of moles of NaOH is just the concentration of NaOH times the volume of NaOH, right? And so the question is right, what is the volume of NaOH that makes this happen, right? That makes this equality work, right? Right? What is the volume of NaOH I have to add in order for these number of moles to equal? And so I just got to solve this equation, right, where I have the concentration here 0.2 molars, right? The volume of HBr, we'll convert it to liters just to be consistent with other problems, right? 0.02 liters, okay? That's molar, liters, right? Then equals concentration of NaOH, okay, which is 0.1 molar times then the volume of NaOH that we're trying to solve for, right? And so you multiply this out, right, and you get 0.004, right? And then you divide, and that equals 0.1 times the volume of NaOH. So you divide 0.1 over, right, and you get 0.04 liters equals the volume NaOH, right, or 40 milliliters, right? If you convert the liters to milliliters, right, you get 40 milliliters. Right? You could have left the volume in milliliters and you would have ended up with milliliters, but I like to do my volumes in liters just to be consistent, make sure I'm never going to run into a problem with not converting. Okay. Right. But that is how I could find, right, this relationship here, right? It's how I can find when I reach equivalence point for any titration with an acid and a base, right? And it's just related with the volume and concentration of the acid equaling the volume times concentration of the base, right? So questions about this example here? Right. So if we want to talk about the titration of a strong base with a strong acid, okay, you have a very similar titration curve where you initially have no acid in solution and just the strong base. And then you slowly add the acid, which lowers the pH, okay? So you get near equivalence point, then you have a very large change in pH. At the equivalence point, the pH is equal to 7. And then past the equivalence point, you're just adding an acid to water. So you're just diluting your acid. So you're just making a more and more acidic solution as you keep on adding more and more acid to that solution. Okay? But, right, if you look at this curve, I'll come back to it, right? Compared with this curve, right? It's basically the exact same thing, just flipped, right, on itself, right? For the strong acid titrated with the strong base, right? You started at a low pH, ended up at a high pH. In this case, we start with a strong base, and we're adding a strong acid. So we start at a high pH and end up at a low pH. Okay. Okay. Any questions about this titration curve? All right. Again, missing. Should have a title here. But, okay, so this is formatted. Is there a question on Zoom? I heard something. Oh, no, I just deleted the title. Okay. I guess I just didn't put a title for the slide. Oh. Whoop. That just disappeared. All right. So this example here is going to be the titration of a weak acid with a strong base. Okay. So this is a pH or a titration curve, right, for a weak acid, strong base titration. Okay. We have the same phases of titration, right? We have the initial phase where there's just the weak acid solution, right? You have a weak acid solution, the pH is going to be less than 7, right? You have some intermediate phase, right, where you've added some of your strong base that's reactive to the weak acid, and you have a change in pH here, okay? Then you get to equivalence point, right, where you see a much larger change in pH, okay? Right? and then once you get past the equivalence point, you then are just adding a strong base in solution, and it's become then a very basic solution, right? So these pictures, right, are to represent these different phases, right? Initially, just the weak acid. I've added some strong base that's reacted with my weak acid to form the conjugate base, and say Na plus here for the strong base being sodium hydroxide left in the solution, right? At equivalence point, I've reacted all of my weak acid. I'm then just left with the acetate ions and sodium ions. And then afterwards, I just keep on adding sodium hydroxides in solution, which just add hydroxides to make it more basic, right? So one of the big differences that we'll notice here is that at equivalence point, right, the pH is no longer equal to 7. Okay? The reason why it's no longer equal to 7, right, is at equivalence point, okay, my salt that's left is sodium acetate. Well, acetate ions in that salt are weak bases, and so those weak bases will react with water to form a basic solution. Okay, so the pH at equivalence point for any titration of a weak acid with a strong base will always have a pH greater than 7, right, at the equivalence point, right? If I'm titrating a weak acid with a strong base, my pH is always greater than 7 at equivalence point, because at the equivalence point, the strong base reacts with the weak acid to form a weak base in solution, and that weak base in solution causes the pH to be greater than 7. Okay, right? And then the other thing to note is in these intermediate concentrations, you've actually formed a buffer solution, right? Because some of my weak acid has reacted with the strong base to form the weak conjugate base. And so then I have a solution of a weak acid with its conjugate base in solution. And that is, by definition, a buffer solution. Okay. So in the intermediate ranges, your solution will become a buffer solution. Okay. And we can use the Henderson-Hasselbalch equation to calculate the pH in this area here, right? And then at equivalence point, the pH is determined by the weak base equilibrium of your conjugate base. And then past that, the pH is determined by the concentration of the OH that the sodium hydroxide that you added to the solution. Okay? So questions about this titration curve? Why the equivalence point is greater than 7? All right. So again, for weak acid, strong base titrations, it's the same type of thing. First, react your acids and bases together. Then, if you have an equilibrium that's established, right, either use ice charts or Henderson-Hasselbalch equation to try to calculate the pH based off of what's left in solution. Okay. Right. So, for example, okay. Boy. Oh, come on. Where did that go? Somehow off the screen that I can't even see it. Close slide. There we go. Share this. Let me reshare the screen. Ah, come on. You can still, but that'd fix it. All right, well, close this again. Just share that. So I wanted to go to anyways. All right, so this is our example problem here. I have a 0.03 molar solution of benzoic acid, which is a weak acid, given the Ka here, right? And I have 0.05 liters of this weak acid, right? I'm titrating it with a strong base that has a concentration of 0.015 molar, okay? And then we're wondering, what is the pH after I've added, say, 0.05 liters of sodium hydroxide, or say 0.1 liters of sodium hydroxide? look at part A here, right? Well, what we have going on in the solution, right, is we have our weak acid. I'm just going to call it HA, so I don't have to write out HC7, H5O2, right? I'm going to just call this HA, okay? My weak acid. It's going to be reacting with the strong base, sodium hydroxide, okay? Right, to form NaA plus H2O, right? That is the reaction that's going on between my weak acid and my strong base, okay? For part A, right, I have a 0.03 molar solution of my weak acid at 0.05 liters, right? So the number of moles initially for HA is 0.03 times 0.05, 0.0015, okay? And then for sodium hydroxide, I have a concentration of 0.015. I've added 0.05 liters, okay? And so that's going to be 0.05 times 0.015, which is going to be 0.00075, I believe. Okay. Okay. I initially start off with no Na plus A minus, and water we just don't even care about. Okay. Right? So questions about where I got these initial moles, right? These are all moles. Right? This initial change final, right? If I'm going to completion, right, I'm not using an ice table. I'm calculating things to completion. I need to use moles for this and not concentrations. Okay? So questions about where I got those moles. Really wish to see the chat. I never should have moved that in the first place. Right. So if you have questions on Zoom, you're just going to have to speak up because I cannot see the chat window. Yeah. All right. Right. So this is going to go to completion. Right. So I have the limiting reagent is sodium hydroxide. So I'm losing all of this. Right. I'm going to lose all of that, or not all of that. Sorry, just 0.0075 moles of that. And then I'm going to gain 0.00075 moles of sodium acetate, or not acetate, sorry, sodium benzate. So HA, I'm going to have 0.00075 moles of that left. I have none of my sodium hydroxide left, and now I've gained 0.00075 moles of NaA minus, right? In this NaA minus, right, we don't care about the sodium, right? NaA minus, right, or NaA, right, just forms Na plus A minus, right? A minus is just, right, A minus is equal to your C7H5O2 minus, right? It's this conjugate base of your weak acid here, so just remove an H plus, you get C7H5O2 minus, right? That is your weak base, right? That paired up with sodium, it's a strong electrolyte, okay? And so, right, and I don't really care about the sodium, right? So really, this is telling me I have 0.00075 moles of Na or of A minus in solution, which again is the conjugate base of my weak acid. So I have a weak acid and conjugate base in solution, which means I can use the Henderson-Hasselbalch equation. pH is equal to the pKa plus log concentration of the base divided by the concentration of the acid, right? So, right, I'll use a little trick here in the fact that, right, these are concentrations. Right now we just have moles, okay? right? If I wanted to get the concentrations, I'd divide each of these moles by the total volume. But because the total volume is the same between these two things, I can use those moles in this equation here. Okay, so this is the pKa plus the log of the amount of my base is 0.00075. Amount of my acid is 0.00075. Okay, these are identical to each other. Okay, which means that this pH equals the pKa plus the log of 1. Log of 1 is equal to 0, so the pH just equals the pKa, which is the negative log of the Ka, which is 6.5 times 10 to the minus 5. Okay? So pH is just the negative log of that number. Okay? You calculate that, you'll get pH equals 4.19. Okay. Which again is just the pKa. All right, so questions about how we did part A here.
Why is the final moles of HA 0.0075?
Why is this 0.0075 of HA?
Yes.
I got that by doing 0.0015 moles of HA minus the amount I have to lose because of its reaction with the sodium hydroxide, which I had 0.00075 moles of sodium hydroxide. And so if you subtract that off, I think I did my math correctly, that 0.0015 minus 0.00075 equals 0.00075. Okay. So yeah, so I got this by just taking the difference of the initial concentration or the initial number of moles of HA minus how many moles of HA I lost in this problem. Other questions? Right, for part B, it's a similar approach, right? We're just now doing 0.1 liters instead of 0.05, okay? But this exact same setup, right? Type of a thing, okay? We got to react stuff, then we got to figure out what's left in the solution, and then calculate the pH based off of that. Okay? How can I share this screen now? Expand this. Let me see. Oh shoot. Sorry, I'm trying to figure out how to share this slide with the people on Zoom. I can't seem to see that stupid window. What? How did that get pulled up? I don't even know. I can't find the thing on Zoom. It's been pulled off to the side. Oh, maybe now? Just let me see. No, the meeting controls are still in the middle of nowhere. All right, that's really annoying. All right, so because of what happened with the meeting controls, there we go. I can just, okay, I'll just do that. There. I can now go back to this, start a PowerPoint. All right, I don't really want to close the Zoom session because I don't want people to log back in and stuff. So so if I switch between screens, it's going to take a little bit longer, but I can get it going. All right, so back here, right? So, and the note here is that the volume of A that was added ended up being halfway to the equivalence point. And for a titration of a weak acid to the strong base, when you're at halfway to the equivalence point, the pH just equals the pKa. Okay, right? So we go back to like our titration curve here, right? So the equivalence point is at 50 milliliters, at 25 milliliters here. Okay, so halfway to that equivalence point is 25 milliliters. The pH of this solution will equal the pKa of your acid, of your weak acid. Okay, so that tells me the pKa of acetic acid here is close to 5, right? Right, based off of kind of going to half the equivalence point and seeing what the pH is. Okay, that pH is equal to the pKa, right? When you're halfway to the equivalence point. Okay? That's true again for a weak acid being titrated with a strong base. Okay, that the pH will equal the pK at halfway to the equivalence point. Okay? So here are just some different titrations of different weak acids with the strong base, where the only difference between the weak acids, okay, is that the Ka of those acids are smaller and smaller and smaller. Okay, the Ka being smaller is indicating what about the acidic strength of that acid? Does smaller Ka mean a stronger acid or a weaker acid? A weaker acid, yeah. So smaller Ka is going to be equal to a weaker acid, okay? Right? So as I'm going up from black to red to green to blue to darker blue, right? Right, my acidic strength is getting weaker, right? Which is why the starting pH is getting higher, okay? And what that also means is that the pH at equivalence point also gets higher and higher, right? Because the weaker my acid is, the stronger the conjugate base is going to be at equivalence point, right? So right at equivalence point, you've reacted all of your weak acid and you just have the conjugate base in solution, right? And so the conjugate base is what's determining the pH. And so as I have a weaker and weaker acid, the conjugate base gets stronger and stronger. So the pH at equivalence point gets higher and higher, right, as I get to weaker and weaker acids. Okay. Right. So questions about these pH curves here. Again, the different curves here are different acidic strengths. Okay, everything's being titrated with a strong base. Okay. We're mainly comparing kind of what the pHs look like initially and at equivalence point, right? You notice after equivalence point, right, all these things have basically the same pH, because after equivalence point, the thing that's determining the pH is the concentration of sodium hydroxide, right, which is independent on the acid that was used initially, okay? So all of these will have the same pH after equivalence point, right? But at equivalence point, the pHs are different, okay? And before equivalence point, the pHs are going to be different because of the different strengths in the acids. All right. The pH at equivalence point of a titration between a strong acid and a weak base will be, what do people think? So if you have a strong acid, right? So you have a weak base in solution, you're titrating it with a strong acid, okay? You think that pH is going to be equal to 7, greater than 7, or less than 7? Less than 7, right? So this is going to be the exact opposite of what happens with a weak acid, strong base, okay? When I titrate a weak base with a strong acid, at equivalence point, that strong acid is reacted with all my weak base, and I'm just left with a weak acid, the conjugate acid to that weak base in solution. and that will lower the pH. And so we see here, the pH will be less than 7. Okay, right? Right. Again, for example, my weak base is NH3. I react NH3 with HCl to form NH4 plus and Cl minus in solution. The NH4 plus can react with water to reform NH3 and H plus ions in solution. Right. This is a weak acid equilibria, right? And that was introducing H plus or H3O plus ions in solution, right? Which is lowering the pH. The pH is less than 7 at equivalence point for a strong acid, weak base titration. So neutral, like strong acid, strong base is pH equal to 7 at equivalence point. Weak acid, strong base is a pH greater than 7 at equivalence point. And strong acid, weak base is a pH less than 7 at equivalence point. Questions? All right. So then which of the following titration mixtures will produce an equivalence point pH which is less than 7? C, right? Yeah. So C is the only one that's going to have a pH less than 7. A here, you have a strong base, the strong acid, right? So that's a pH of 7 at equivalence point. Here you have a weak acid with a strong base. That's going to have a pH greater than 7 at equivalence point. Here you have a weak base with a strong acid. pH is going to be less than 7 at equivalence point. And then for D, you have a strong acid with a strong base again, so pH equal to 7 at equivalence point. So C here is the only one with the pH less than 7 at equivalence point. So which of the following will produce a titration mixture with the pH less than 7 at equivalence point? Again. B, right? So HF is a weak acid, BaOH2 is a strong base that will have a pH greater than 7, okay? C, you have a strong acid, strong base, pH equal to 7 at equivalence point. D, you have a weak acid, strong base, so that's going to have a pH greater than 7 at equivalence point. And then NC5H5 is a weak base, okay? Maybe not one we're familiar with and used too often, but that is a weak base, so that reacting with a strong acid will have a pH less than 7 at equivalence point. Okay? So B here. All right. So what is this titration curve of? A, a strong acid titrated with a strong base. B, a strong base titrated with a strong acid. C, weak acid titrated with a strong base. Or D, weak base titrated with a strong acid. Yeah, so it's going to be A, strong acid titrated with a strong base. pH is 7 at equivalence point, and I start off with the acidic solution and end up with a basic solution. That tells me it's A. And what about this one? B, right? Strong base to strong acid. Again, a pH of 7 at equivalence point. And then I start off the basic solution and then end up with a acidic solution. Okay. This one. C, weak acid with a strong base. So I have a pH that is greater than 7 at equivalence point. Right, and I start off with an acidic solution, end up with a basic solution, right? And then this one, D, right? Weak base with a strong acid, so my pH is less than 7 at equivalence point, okay? And I start off with a basic solution, end up with an acidic solution. Okay. I guess a lot of these you got a hint by what is the x-axis, right? The titrant was on the x-axis for all of these, which is a strong base, strong acid, strong base, strong acid. Kind of knew what they had to be based off of that as well. But questions about these curves? Right, another type of titration that we might deal with are polyprotic acids. Okay. So for polyprotic acids, right, we have multiple equivalence points because you have multiple acidic protons. Okay. So right, for H3PO3, for example, okay, right, I start off with H3PO3 in solution, right? It's acidic. It's donating one of its protons in solution. It's a weak acid. Okay. It undergoes a titration with a strong base. When I reach the first equivalence point, right? Okay. And I've added equal number of moles of NaOH as I have H3PO3. Okay. Then I've reached this equivalence point, at equivalence point, and now just have H2PO3 left in solution. But that itself has another proton that can donate. So it, again, undergoes what looks like another kind of weak acid, strong base titration. Okay. But now it's at a higher pH because H2PO3 is a weaker acid than H3PO3. Okay. Right. Each additional proton that you remove is a weaker and weaker acidic proton. Right. And so that's why the pH is higher up. Okay. And again, I have the same titration of a weak acid with the strong base. I reach then the second equivalence point where I've added twice now the number of moles of sodium hydroxide as I did H3PO4, right? Because the first equivalence removes one of the hydrogens. The second equivalence removes the second hydrogen to then leave me with HPO3 2 minus, okay? And then I titrate that, right, with a strong base, okay? And I would eventually reach a third and final equivalence point, okay, with, somewhere way out here, right, with the removal of the final proton from this polyprotic acid here to produce PO3 2 minus at the very end. Okay. All right. So, but the titration of polyprotic acids is like that of a strong acid or weak acid titrated with a strong base. The only difference is you just have multiple equivalence points along the way. Yeah.
So the amount of hydrogen ions on the photo side we found that you see
Say that again.
So like there's 3 hydrogens from start. So going from left to right, you're going to get 3 equivalents. So how many hydrogens is how many?
Yeah. Yeah. So for polyprotic acids, right, the number of acidic hydrogens that you have is the number of equivalence points that you will get. So this will have 3. The third one's not really plotted here, but this will have 3 equivalence points, right? If I did like H2SO3, there will be 2 equivalence points because it has 2 acidic protons, right? So yes, the number of equivalence points is equal to the number of acidic protons that you have. Okay. Right. Right. And if you knew, say, the first equivalence point was at 50 milliliters, you know the second equivalence point has to be at 100 milliliters. Okay. Because right, you're just removing another proton. You have the same kind of initial concentrations and things like that, right? So, right. So it has to always, right. The next equivalence point is going to be at 150 milliliters of sodium hydroxide, right, for the third one. Okay. So, other questions about titrations of polyprotic acids? Right. And then just a reminder for indicators, right, for when you're doing these titrations in the lab, if you haven't done so already, right? If I have some sort of indicator like this, right, where on the reactant side it is a red color, on the product side it's a yellow color. The question is, what will this indicator be in acid versus, say, what color will the indicator be in the basic solution, right? So in acidic solution, what color will this indicator be? red, right? Because in the acidic solution, I've added a lot of H pluses to that solution, right? There's a lot of H pluses floating around, so it's going to shift this equilibrium to the left, which is going to form a lot more of the HN species in solution, which is a red color, okay? And then in basic solution, right, it's going to be yellow because I've removed a bunch of H pluses, so now it's going to shift the equilibrium to the right to try to reproduce these H pluses in solution, okay? And so I'm going to form a lot of IN minus, which is going to have a yellow color to it. Okay. Questions about that? So I don't want us to start KSP today. What we can do is just go over one more of the examples that we did today, right? We only did part of the 2 examples that we kind of focused on today. And so let's do screen. All right. So I don't know if anyone has a preference from if we want to continue on from this first example or the second example. Second one. All right. Let me grab a blank piece of paper. Do this. All right. So let's do part B in this example, right? So part B for this example, we have still this HA, as I'm going to call it, reacting with NaOH, form NaA plus H2O, okay? But now, right, my initial concentration, so this I still have, if we recall, right, the initial concentration, this was 0.0015, okay? Right, which again, I get that by taking the concentrate, or sorry, the initial number of moles of HA, right, is the concentration of HA times its volume. Now I'm going to do the same thing for NaOH, take its concentration of 0.015 times its volume of 0.1, okay? And that is going to give me 0.0015 moles, right, of NaOH. 0, and we don't really care about water. Okay. Right, well, in this case, I have equal amounts of moles of HA and NaOH. Right, so both of these, I'm going to lose all 0.0015 moles, and I'm going to gain that many 0.0015 moles of my NaA compound, right? So at the end, 0.0015, right? So this actually, part B here, is at the equivalence point, right? So part B is the equivalence point for this solution, okay? Because I've added equal moles of my strong base as the weak acid that I had in solution. And again, I get the moles from the concentration times the volume. Right, well, what's left in solution is Na plus A minus, right? And I have 0.0015 moles of each of these, right? A minus here is our conjugate base, which is a weak base, right? The conjugate base of a weak acid is a weak base itself, right? And so in this solution, the only thing that's left in solution to determine the pH is the weak base. Okay? So to get the pH of the solution, I got to find the pH of a weak base, right? Now this is the number of moles of A minus, right? I want to find the concentration of A minus in solution, which I get that by taking the number of moles, 0.0015, and dividing by the total volume of my solution, which was the initial volume of 0.05 liters plus my added volume of 0.1. So this is 0.15 liters, Okay, this is moles. So that comes out to be 0.01 molar, right? Yeah. Okay. So I have 0.01 molar of my conjugate base, my weak base in solution, okay? And so in solution, A minus, right, will react with water, form HA plus OH minus in solution in this weak base equilibrium reaction, right? That's what a weak base does in the solution, right? Weak base will react with water, form hydroxide ions and its conjugate acid in that solution, okay? And so this then becomes an ice table problem, ice chart problem, right? Because now I have some equilibrium of a weak base, right? I can't use the Henderson-Hasselbalch equation because I have 0 amount of my conjugate acid, right? My weak acid is at 0. I've reacted off all weak acid with my strong base, so I got none left. All that's left is the weak base in solution, okay? And so this initial concentration is 0.01. Don't really care about water. Initial concentration of HA is 0, again, right? And then OH minus, none of that initially, okay? Right, the change here, I'm going to lose some X amount here, gain some X here. It's going to be 0.01 minus X, X, and X. Right. Okay. We're going to approximate this, right? It's just 0.01, okay? And we need to plug that into the KB expression, right? KB equals concentration of OH minus times concentration of HA divided by concentration of A minus, okay? Now the problem is in this problem, we're not given KB, okay? We're given Ka. So how do I calculate KB, the numerical value of KB? Right, KB, exactly, from KW divided by Ka, okay, which is 1 times 10 to the minus 14. And then Ka in the problem that's given is 6.5 times 10 to the minus 5. Okay. So this comes out to be, so Kb is, do it down here, right? Kb equals, and you plug in those numbers, 1.5 times 10 minus 10, okay? So 1.5 times 10 minus 10 equals concentration of OH times concentration of HA, which are both X at equilibrium. So X times X divided by my concentration of A minus is roughly the 0.01, okay? And so then X squared equals, multiply 0.01 onto the other side, 1.5 times 10 to the minus 12, okay? And so X here is equal to the square root of that 1.5 times 10 to the minus 12, okay? Which is, okay, and so in this problem, X equals 1.2 times 10 to the minus 6, okay? Which that X, again, is the equilibrium concentration of OH minus. So this is equal to the concentration of OH minus. Okay, so I can get, say, the POH by taking the negative log of 1.2 times 10 to the minus 6. Okay. That gives me a POH equal to 5.92. And then I can get pH plus POH equals 14, right? This up here, right? To then get that the pH is 14 minus 5.92, which is 8.0. So that is the pH of the solution, which is at equivalence point, which, as we've said, it needs to be. We do find that it is in fact greater than 7. It's at 8.08. Okay. So this is definitely one of the more long, complicated titration problems. Okay. When you reach equivalence point between a weak acid and a strong base, right, you're just left with a weak base, and then you need to use an ice table because you just have weak base in solution to then calculate the pH, right? Well, in part A, we use the Henderson-Hasselbalch equation because we had both the weak base and the conjugate acid. Okay? Questions about this example, how we did what we did, why we did what we did? Okay. The steps are fairly straightforward in these problems, right? React your acid and base together, figure out what you have left in solution, calculate the pH based off of what's left in solution, right? But there are a number of steps, right? So kind of, right, the direction of the steps is straightforward, but doing them takes some time and potentially a lot of work, right? All right. So questions about this example, about titrations? Again, if you're online, if you have questions, you're going to have to speak up, or I'll stop sharing the screen in a second and be able to see. For those who are in class, if you'd like to pick up your exam, you can. I have the forms or the exams here. I'll try to split them here into forms. So form 1 and form 2, they're not organized any other way besides forms, but you can pick them up. And then again, don't forget to turn in your participation questions as you leave on the back table. Let me see if I can't stop sharing that screen here. Okay. All right, so now I see the chat. I don't see there's any questions in chat, but if there are any other questions on Zoom, feel free to ask them now. I'll wait a minute. All right, doesn't seem like it, so I will see you guys on Wednesday.